Hi, welcome to another weekly session. And today's topics are extremely interesting and they are widely used, practically applicable topics. We are about to discuss MobileNet. Yes, we are about to discuss MobileNet. Then we proceed to EfficientNet architectures and then finally wrap up the session with understanding what EfficientNet architectures are. So in MobileNet architectures, what happens is they are extremely computationally efficient. And being so computationally efficient, they are being utilized. They can be utilized on mobile devices. But on mobile devices, we can utilize MobileNet architecture. So what makes them the first choice to be utilized on mobile devices? The reason being the computational efficiency they are able to provide by multiple times. So if a standard convolution neural network is there, for such a standard convolution neural network, if an analogous MobileNet architecture is prepared, it would be 7 to 8 times less computationally expensive. Less computationally expensive, by less computationally expensive, I mean it would take up less number of parameters, and by less number of parameters, it would be way computationally faster. So not only training, but also in the inference, when you're doing the inferencing, the model would be extremely fast. And that is what sets apart MobileNet architecture from the rest of the classes. Till then, we have not discovered EfficientNet architectures. EfficientNet came up back in 2019 and MobileNet was there in 2017. So MobileNet was a great invention of its time, and it was the first choice of be it a data scientist or a non-data scientist. Everybody would be using MobileNet architectures. But what goes behind it? Why everybody is running after MobileNet architectures? The reason behind it is this. That is what we are about to discuss. So that is a depth-wise convolution layer. So what is depth-wise? A standard convolution layer is something you already know. So you define the number of filters and it goes through overall the input. But in depth-wise, what it happens is takes the depth channel, it takes the feature channel, and it convolutes over it and generates a corresponding output filter, output feature map. So if you have RGB channels, it would generate 3 channels. If you have an intermediate 3 layers, 4 layers, it would generate 4 as a 4 feature maps. Rather than making an amalgamation of it and making of, so it is working on the depth wise, on the feature wise. Once it works on the feature wise, then it goes through a point wise 1x1 convolution. 1x1 convolution is something you saw back in EfficientNet architectures. So in EfficientNet architectures, that is something you must be familiar with. So that is what this paper mentions. If you go through it, it does all the calculation extremely easy to understand. It reduces by 1 by n plus 1 by kernel size square, which is approximately equal to 8 to 9 times less computation if you are using a 3x3 filter, kernel filter. So that's what this paper about. And let's start with the implementation. So we have two things. First is the architecture, and within every architecture we have a repetitive pattern, which is the block unit. This is the block unit. So let's start with the block unit first. So first we have a depth-wise convolution. Then we have a batch normalization. We have a ReLU layer. We have a convolution. And that's it. In depth-wise convolution, we have TF Keras layers, depth-wise convolution 2-dimensional, kernel size, strides, padding. Kernel size is 3x3. Strides equals to strides. What else? Padding equals to same. Padding equals to same. Then we have a batch normalization layer, TF Keras layers dot batch normalization. Then we have a ReLU layer, TF Keras layers dot ReLU. We have a convolution layer, TF Keras layers dot convolution 2-dimensional, wherein it is a 1x1 convolution. Filters would be filters. Kernel is 1x1. Stride is something that needs to be mentioned. as a parameter. Good enough. Let's start with the implementing the call function. So call would be x goes through first a depthwise, followed by a batch normalization, followed by a relu, followed by a 1x1 convolution, followed by batch normalization, and followed by a relu, and you return the output. Now let's get to the main structure. Within the main structure, we have such repetitive patterns wherein a single unit of convolution happens, then our repetitive blocks keep on happening. So after every convolution, we have a batch normalization and relu, which is not mentioned explicitly, but it is there. It's an implicit statement. Addition to this, we have average pooling, fully connected layer. So let's keep on implementing self.convolution equals to tf keras layers dot convolution 2-dimensional, and we have filters as 32, kernel size 3x3, strides as 2, padding equals same. Apart from this, we also need to implement average pooling, self.average pool, which is tf keras layers dot average. Come on, drop the suggestions. Average pooling 2-dimensional, wherein the pooling size is 7x7 with strides as 1. Now let's define the call unit. In the call function, what we have is it goes through the first unit, it goes through, we need a relu. We also need a batch normalization. Self.conf, self.batch normalization, self.relu. Then the repetitive units. So the first unit is x equal to MobileNet block, wherein the parameters are 64 filters, stride as 1, filter stride as 1, which goes forward to another MobileNet block with 128 filters, stride 2. It now goes to another one with 128 and stride 1, another one with 256, stride 2, another one with 256, stride 1. Finally, 512, stride 2. The loop of 5 units. Five, 1, 2, comma 1. Then we have 1024 2. I think strides is always 1 for the second part, isn't it? Yeah, it is always 1. So let's mention 1 over here. And yeah, so we are done with the loop. Once you're done with the loop, it goes through 1024 to another 1024 to finally with an average pooling finally with a dense hey, did I mention the dense on average pooling over here? I mentioned the average pooling, I didn't mention the dense. So let's mention the dense layer over here. tf keras layers dot dense 1000 activation equals softmax. I think we're good to go. What happened? Return. Yes. And here we are, finally completed with the Mobilenet architecture. This is the Mobilenet architecture. This is what you would obtain. Not good enough to understand and comprehend, but this is what it is. But this is quite understandable. Whatever you did over here is quite understandable, legible, and comprehensible. So whatever it is, Mobilenet architecture is one of the best architectures utilized by all of the people for its fast computational power. But we now have EfficientNet architectures, which we'll talk at the end of the video. But these architectures were designed to expedite the computational process, which happens on the edge devices or on the mobile devices. So if you have a MobileNet, if you have a deep learning model which you want to use it on a mobile phone, most probably you will be using Mobilenet architecture. Most of the people use Mobilenet architecture for your mobile devices, but nobody knows what actually goes behind it. The main reason which boosts the Mobilenet architecture's performance is the depth-wise separable convolution layers, which is a depth-wise convolution followed by a 1x1 point-wise convolution, which reduces the computation cost by a extremely high factor. So that's what it was. Let's proceed to implementation of Xception architectures, and ensure that you do hit the subscribe button. Hit the subscribe button down there in the links, and take care. Do ensure that you check out the data science in a website. Take care. Bye bye. Hi, now let's start with implementation of EfficientNet. Now this EfficientNet architecture works on extremely similar lines with what we saw in MobileNet architecture. MobileNet architecture utilizes the efficiency of depth-wise separable layers. So does this particular architecture does it also uses separable layers. What's the difference? Difference between how the architecture flow is designed. It is designed in three parts. First part is entry flow, second part is middle flow, third part is exit flow. In the entry flow, we have a certain kind of architectural design. In the middle flow, we have a certain kind of architectural design. In the exit flow, we have a certain kind of architectural design. Apart from it, both of the MobileNet architecture as well as the EfficientNet architecture, both of them use the concept of separable layers, separable convolution layers. Explicitly, if I were to mention explicitly the MobileNet architecture, if I were to mention explicitly, the MobileNet architecture uses depth-wise convolution 2D, which is TF Keras layers depth-wise convolution 2D. And if I were to mention about this particular layer, about the one which EfficientNet uses, it is separable convolution layer. There's a difference between the two. Slight difference between the two. No, not so massive, but a slight difference. So let's get started. So this is what the official paper is. After every convolution, you have a batch normalization. So is the case with after every separable convolution, you have a batch normalization, and we have three flows. This is mentioned over here. After every convolution, we have the batch normalization. Separable layer user depth multiplier 1, and yeah, this is the architecture. Entry flow, middle flow, exit flow. Entry flow, middle flow, exit flow, and if this code runs successfully, we will be good to go. Although this won't fetch us with model.summary, but this is a good way to understand how the architecture is built. And with complex architecture, it's better to follow an object-oriented approach rather than going for the standard methods. So let's start with convolution batch normalization. Self dot convolution equals to this. Self dot batch normalization equals to this. Wherein TF Keras layers dot convolution 2-dimensional. Here I have filters equals to filters. Kernel size equals to kernel size. Strides equals to strides. TF Keras layers batch normalization. In the call function, you take the input, pass it through a convolution first, take the input, pass it through batch normalization, and you finally return it as the output. So is the case with separable batch normalization. You have two layers sep, you have batch normalization, TF Keras layers. Come on, give drop suggestions. Here we are. Filters equals to filters, kernel size equals to kernel size, and we have strides equals to strides. In batch normalization, we have this. In the call, you can call the functions, you can call the layers, and return the output. In the entry flow, now the main game begins. This is just the preliminary part. You have defined the building blocks. Building block is a convolution batch normal normalization and a separable bash normalization. That is the building block. Now let's get to the main part. The main part talks about entry flow, middle flow, and exit flow. So let's start with entry flow. In entry flow, I get started with the bash normalization layer first, then I have a relu. Bash normalization is defined before, so I need not to define it in the init. Bash normalization is defined, relu is not defined, so let's define relu. Self.relu. Max pooling is not defined. Let's define max pooling. Apart from this, everything else is defined. So you see, this entire is one unit, but we'll not skip so many steps since this is a new concept. I'll try to implement step by step. You can combine these into another unit building block, these into one building block. That's up to you. That's up to your efficiency, proficiency. But my task is to explain the things to the maximum clarity, and that I'll try to do. So we have here relu function. Here we have tf keras, layers, max pool, 2D, 3x3. Stride is 2x2. Now let's start. First, a convolution. Filters 32. Kernel size 3x3. Stride 2x2. Then we have a relu. Again we have convolution bash normalization. Strides 1x1. From here it bifurcates into two paths. The first path is take the X, pass it through a convolution bash normalization, wherein the number of filters I'll get to the number of filters. Kernel size is 1x1, stride is 2x2, it goes through X. The other path, on the other hand, goes through a series of operations, which is first is its separable bash normalization, wherein we have 128 filters. Kernel size is 3x3, stride is 1. This goes through a relu. This goes through another separable batch normalization with 128, 3x3, we have done till here. Now let's proceed to max pooling. Finally, we have max pool, wherein it goes through the path 2. Finally, you would also need an add layer for concatenation purposes. So my X becomes self.add with path 1, path 2. Here we have 128 filters so that it is able to concatenate. Based on this, a similar architecture is to be made for the remaining two parts. Path 1 would be convolution patch normalization with 256 filters, 1 cross 1, 2 cross 2, x. Path 2 is nothing but self.relu x. Path 2 is also followed by a separable batch normalization, which again goes through a relu unit. Followed by a separable batch normalization, followed by max pool, finally we again have a split, and the split will be calculated by 728 filters. So path 1 is this part is the path 1, the left side division is the path 1, this is the main flow, this is the split connection. So 1 cross 1, 2 cross 2, x. Path 2 is self.relu x. Path 2 is separable batch normalization 728 3 cross 3. Path 2 is also equal to self.relu path 2 is also equal to separable batch normalization 728 3 cross 3. Path 2 is also equal to self dot max pool path 2. Finally, you obtain the output, and that is the result of concatenation of path 1 and path 2. So we are done with our entry flow. Now let's proceed to middle flow. It's shorter to write as we have a for loop over here. Nothing much, just a relu tf keras layers dot relu. Good enough. So what do we have over here? For this in range, how many times? 8 times. Repeated 8 times. 8. What we have is path 1 would be equal to x, whereas path 2, here we don't have any convolution network. Path 2 is self.relu x. Path 2 is also equal to separable batch normalization with 728 filters 3 cross 3, which is then followed by another relu layer and a separable batch normalization with 728 3 cross 3. Path 2 is also equal to self relu with path 2. So we have used 3 relus. Final separable batch normalization is left with 728 3 cross 3 path 2. Self.add is left. Self.add equal to tf keras layers dot add. So this would be my new x, addition of path 1 and path 2. Once this is repeated for 8 times, we are done with it and we return the output. That is the middle flow. Now let's proceed to the exit flow. In the exit flow, the fundamental units are relu, Separable is there, convolution is already defined, max pool we need to define, relu we need to define, add we need to define, and global average pooling we need to define, and a dense layer we need to define. So there are few many things we need to define. Separable.relu, which is equal to tf keras layers dot relu. Then we have max pooling, tf keras layers dot max pool 2D with 3 cross 3, 2 cross 2, padding equals to same, and we have global average pooling, which is tf keras layers dot global apart from it a final dense layer for the classification part. And finally we might need add for the addition parts, for the concatenation parts. So tf keras layers dot add. Good enough. So let's proceed with the flow. First, a bifurcation, path 1 equals convolution batch normalization with number of filters we'll get to. We have 1 cross 1 and 2 cross 2, which goes through X. In path 2, something similar happens. It first goes through self.relu. Something not similar happens, something similar to what has happened before happens. Path 2 then goes through separable batch normalization, wherein we have 728 filters, 3 cross 3 as the kernel size, and it goes through path 2. Path 2 then heads forward to another relu layer. Come on, when will I stop doing this? And then we have separable batch normalization. We have 1024 units, 3 cross 3, path 2. Path 2 is followed by a max pool with path 2. This goes through an addition followed by a separable batch normalization with 1536 and 3 cross 3. This also goes through a relu. Finally, a global average pooling layer. And a dense layer. And you're going to return the output. And over here it has to be 1024 so that it matches with this, right? So let's get it done. And yeah, stop calling it as def, it should be class. So should it be class, and this is good. What happened? Kcast, where did I call Kcast? in entry flow we did some mistake, so it is first unit, then it is second unit. In second unit we have 256 3 cross 3, 256 3 cross 3. We forgot to mention, there it be, doesn't matter. Let's rectify this. Yep, and we are good to go. So this is what exactly EfficientNet architecture is all about. You have three parts. You won't be able to see model or summary because it's defined this manner. But good to know, this is a better representation of the architecture. And first we defined the convolution batch normalization, then we proceeded to separable batch normalization. This and depth-wise convolution 2D are extremely similar. There's the high resemblance. The only difference is in a few number of parameters. There's a difference of 10 parameters, exactly 10. So it's good to use this. And the paper asks us to use separable convolution 2D, so you need to use separable convolution 2-dimensional. Apart from it, you go to entry flow, you define the call, you define the middle flow, you define the call, you go to the exit flow, you define the call, and finally you amalgamate the three and get your final output, final model done. Build the model and you're good to go. If there is no error popping, you've implemented it correctly. Yeah, so let's proceed to understanding the architectural design of efficient nets. Till then, ensure that you should have hit the subscribe button. If you're still watching, do ensure that you hit the subscribe button down there in the links. Hi, now let's get started with EfficientNet architectures. EfficientNet architecture is a class of models which try to improve the accuracy as well as the efficiency. Mind the words, which try to improve the accuracy along with the efficiency, which means that they are trying to improve the performance, but they are also trying to reduce number of parameters, which means with a less number of parameters, they are able to achieve a higher accuracy, which also means that with the decreased number of parameters, you are able to achieve a faster computation. So within much lesser time, you are able to achieve a greater accuracy. And that's what EfficientNet architectures are made for, built for, designed for, and that is on a very fundamental intuition. The fundamental intuition behind EfficientNet series. There's a series of architectures. So they started with efficient B0, then it goes to B1, B2, B3, B4, B5, B6, B7. And for all the architectures, that is a model scaling. They try to implement model scaling. What exactly is model scaling? We'll try to understand in a step-by-step manner. They call it, the authors of the paper call it as compound model scaling for achieving a better convolution neural net. So they start off, be it any architecture. Let's say you're talking about ResNet 18. How did ResNet 18 become ResNet 101? By improving the depth of the architecture, right? So why not increase it to ResNet 1000? Why not increase it to ResNet 10,000? Why not increase it to ResNet 10 lakh? Because ResNet 1000 and ResNet 101 achieve more or less same performance, and whereas ResNet 1000 is taking a lot more computation, is computationally expensive compared to ResNet 101. Reason being, we know the reason is theoretically deeper the network, better should be the performance, but we know there's a problem which is known as vanishing gradients. So vanishing gradients is there, and that is inevitable. Vanishing gradients, the problem of vanishing gradients is inevitable, and for that we have a restriction over the depth. So no matter how, to one extent, if you increase one parameter, to a certain extent, you will be able to achieve a better performance, better accuracy. But after you're doing like, you've increased the depth to a certain extent, then after that, there will be a saturation. Once the saturation is reached, there's no scope of going beyond that. Once the saturation is reached, there's no scope of going beyond that. So what we do, we are trying to go along with the depth, we are trying to scale up with the width, we are also trying to scale up with the resolution. So there are three factors, which one is the depth, second is the width, third is the resolution. So if you increase the depth, or the performance increases. If you increase the width, which was there in the Xception modules, the performance increased. If you increase the resolution, performance increased. So what exactly it is? So what exactly it is? This is basically understanding that what about if we combine all the three factors together and scale it in proportion? So if you're increasing the depth, increase the width, and increase the resolution. So if you take into consideration the three factors and go along with it, then the authors discovered that with the fewer number of parameters, a greater performance is achieved. And yeah, that's what it was. That's what it was. So this is what they are. This is a baseline architecture. Then they are going for width scaling. Then they proceed to depth scaling, resolution scaling, and this is compound scaling: higher, deeper, wider. And this is what majorly it is. So this is the architecture. You can check out the architecture. So what you can do is print out the summary, model summary for different EfficientNet architectures for EfficientNet B0, EfficientNet B1, EfficientNet B2, EfficientNet, all the EfficientNets. You can print out the summary and you can compare how the things are happening. So what they talk about is so they start with scaling up. They start with a baseline model EfficientNet B0 and they start scaling up to B7, and for whatever it is able to achieve a better performance for yeah, this is the main part. So is able to achieve is 8.4 times smaller, this number of 18 times fewer number of flops, which means 5 to 6 times faster, and performance wise also better. This is the main summary of the paper. Now let's get to an topic or medium article. So this is the mathematics behind it. I wanted to talk about this. This paper illustrates the architectural design. So this is the architectural design. So what he talks about is common things which happen in all the architectures. So first thing is in its stem, after all the experimentation with the architecture starts with the common 8 models and the final layers. This is the stem and this is the final layer. Right? Now they have a module type base. So these are the 5 to 6 modules. These are the 5 modules which are repeatedly used again and again. And once these are used again and again, you are able to achieve newer architectures by properly implementing compound scaling in a proper manner, by proper implementation of compound scaling. Now this is basically if you combine multiple modules, that becomes a sub-block. Now what we have is EfficientNet B0 is a block 1, block 2, block 3, block 4, and thereby you have 7 blocks, you get the final layers. Here also B1 has 7 layers, but you are increasing the depth, you are increasing the width, you are increasing the depth, and you are increasing the resolution. So this is what they are trying to achieve. So the proportionate increase happens for the model architecture, and that is the beauty of it. And I don't think there's much to add. All we can do is do a model summary to achieve and see how it goes. Yeah, so let's begin. You can see 7 blocks, and so you can explore. I think this is not a good way to check out from tensorflow.keras.utils import plot model. Plot model, model 1. So this is the architecture. This is not at all understandable. Better illustration is this. I think you're able to get the understanding of it. This is what the EfficientNet architecture is trying to do. If time permits, we will try to implement. But this is a huge architecture, 237 layers for EfficientNet, and B7 has 813. Even with so many layers, it is able to achieve a lesser number of parameters and better accuracy. So that's the beauty of it. Don't make a better accuracy model, try to make it efficient as well. Yeah, so that's what it is. That's what it is. And 5 modules, repeated use, make a baseline. From the baseline, start expanding and scaling up in accordance to your need. And using that philosophy, you're able to achieve different and better architectural designs. So let's wrap up the session over here. Have a good day, and don't forget to hit the subscribe button. I don't understand why people forget to hit the subscribe button. Don't ever forget to hit the subscribe button. Do hit the subscribe button, like and share with your friends, and add any suggestions if you have. Alright, take care. Bye.